Volker Crede. Nines Clemens. Volker, are you ready?
Yeah.
Yes, I can share my screen.
The carpet is for Titi now. I switch off my video.
All right, can you see my screen?
It's perfect. Yeah.
Okay, so then let me just okay, how do I go into full screen if Zoom covers up my
That's not so you need to go in full screen, but then you don't see anything. But I will then
just try Control L.
Try Control
give
L.
you the 5 minutes then warning.
Or Command L if you have a Mac. That should do.
Here we go. Does that work?
Looks good.
All right, perfect. We're all Zoom experienced. Okay, so this talk was originally meant as an introductory talk. So I will skip over most of the introduction and motivation, and a lot of the material has already been covered also by Annika. So, I was asked to give an experimental overview on baryon spectroscopy. I will be very brief in my introduction here. So let me just go right into it. We know that Rutherford gave the proton its name like almost precisely 100 years ago. And then the spectroscopy of nucleon resonances really took off in the 50s in pion nucleon scattering. And these are pictures that I've taken from the particle data booklet, where we see a very prominent peak for the delta resonance. And some structures then all the way up to about 2 GeV, and then sort of the resonance structures fizzle out towards higher energies. And this is a problem that has poised our field to the very day. So these structures consist of many resonances, and the challenge in the experimental efforts is to disentangle the individual resonance contributions. So in this picture here, you see like the pion nucleon scattering results, the cross sections separated into pi plus proton and pi minus proton, and I've indicated here the individual resonance contributions. And in particular for the pi plus proton, you see there are hardly any peaks visible beyond the ground state delta. So that is something in N-star spectroscopy in particular, that is the challenge to disentangle all these resonance contributions. And as Annika has already mentioned, the experimental approach is to use polarization observable and perform polarization measurements, not only in pion nucleon scattering, but in particular in photoproduction. And that's what the experimental community, the low energy experimental community, has been doing for the last almost 15 years now. When it comes to excited baryons, it may be interesting to note that beyond the nucleons and the delta resonances, hardly any of the spin and parities have been measured. So in particular for the doubly strange, for the cascades, and for the omega baryons, no spin or some spin measurements have been performed, but no parity measurements have been made. And that is something that we are like thinking about and that we're trying to prepare, like with GluX data, for example. So all the spin parities that are listed in the particle data booklet are essentially based on just the quark model assignments. And that is interesting to note. So I will skip over the motivation, why we're interested in non-perturbative QCD. I think that's the topic of the workshop. What is interesting is that baryon resonances are not only interesting for our community in terms of understanding how QCD makes these resonances, but in recent years, there have been connections also to more the high energy community, or the community interested in the quark-gluon plasma, where they need more baryon resonances to describe the freeze-out behavior from the quark-gluon plasma. And in particular, like strange baryons and doubly strange baryons are desperately needed in these models to describe this and understand this behavior. What's also interesting is their connection to astrophysics. So for example, this is a measurement that has come out last year from the CLASS collaboration, where we have measured the lambda proton elastic scattering cross-section, which was a challenge because we had to prepare a secondary beam of lambda baryons, and in particular estimating the lambda beam luminosity was a real challenge. But the results improved the world database substantially, as you can see here in this picture. And that has attracted the interest of the astrophysics community, where these measurements may be needed in the equations of state, for example, to describe neutron stars. And given the interest that I've also experienced, like at my own institution from the astrophysics group, we're looking at the moment into repeating these measurements using GLUAX data, extending the momentum range here, and looking into maybe even do these kinds of measurements for cascade proton scattering, which should be doable. It is just a very challenging experiment. So there's a lot of interest still in baryon, in excited baryons, also from other communities, and that's nice to see. So picking up where Annika left off, she already showed the spectrum here. This is the spectrum of nucleon resonances, and Annika already mentioned the excitation bands here. So we see the first excitation band, and in terms of where we are in the field, the first excitation band here on the right, those are the ones with negative parity, the first resonances with negative parity. I think this multiplet, at least for the nucleon resonances, has been mapped out. And the efforts concentrate at the moment on mapping out the second excitation band here with positive parity, where we have the radial excitation of the nucleon, and then those resonances where, when we describe the baryon with these two oscillators, where we have two units of angular momentum, where these two units can either like sit in one oscillator, or each of these oscillators has one unit of angular momentum, just using the simple constituent quark model. And the efforts concentrate on that. The experimental community is still guided by these multiplets. And cautiously saying, I would say that we're very close to like having good candidates for all these multiplets in the second excitation band. I think we're missing, if I look this over, we're missing two resonances here with spin-free half. But other than that, I think we're very close to the goal that we set ourselves. Beyond that, looking at baryon resonances beyond 2 GeV, I think all bets are off. We are looking here at the third excitation band, and I don't think we've made some progress in this area, but there's no dedicated effort to really map out the entire excitation band. We're missing the data for that. We're missing the polarization data to really make progress here. So Annika also showed already the lattice spectrum, and I don't want to go into details here, but at least the lattice calculations at this point, they agree with the constituent quark model in the sense that they predict the same number of states. So when it comes to these missing resonances, the lattice at the moment predicts the same number of states. And that has been a guidance for us to map out these multiplets. Okay, I'll skip over the motivation here. We know that we need these polarization measurements in order to arrive at these so-called complete experiments that our community has been talking about for a long time. In general, how do we study baryons experimentally? I mean, this can be from an experimental point of view, like separated into nuclear physics experiments, like fixed target experiments, photoelectroproduction at JLab, ELSA, MAMI, and so on, where we have gamma nucleon and electron nucleon experiments, or pion nucleon experiments that are ongoing. So this is sort of the nuclear physics community, and we can separate that from the high energy community, where baryons can be studied in collider experiments, plus or minus machines, or in PP reactions. And it's sometimes a little disappointing that the two communities are somewhat separated. and we're doing the same physics, but funding-wise, it's really hard for us to get involved with any of the other experiments. And to my taste, we're just talking too little to each other. Okay, so the NSTAR program has two main components. One is to establish the systematics of the spectrum, so finding new states, and then what we've been doing at JLab at the class experiment is to probe these resonance transitions at different Q-square and distance scales, and that reveals the structure of the NSTAR states. So the class collaboration that has been heavily focused on baryon spectroscopy in the past is now moving on to more the second component here, looking at the structure of these states and mapping out the Q-square dependence, and the core like search for new excited states is slowly fizzling out, as I will show you in a second. So there have been some interesting results coming out. For example, in recent year, the Roper resonance, the Q-square dependence, and the description of these data has sort of ruled out a gluonic excitation for the Roper resonance, and it's clearly identified now as the best candidate we have for the radial excitation of the nucleon. Likewise, there have been efforts for other resonances like the NSTAR 1535. And this is also, these measurements have identified this state as the first orbital excitation of the nucleon. So this is an effort to extend the Q-square range. This is like one of the program in the class 12 experiment and some of the new experiments at Jefferson Lab. Okay, I'm struggling a little bit here with my Zoom. Okay. Okay, so Annika mentioned already the polarization experiments that are needed, and I've always shown in recent years these three ingredients that we need in order to make progress in terms of mapping out the nucleon spectrum: double polarization experiments, and I think in all honesty, maybe speaking on behalf of my community, the experimental community, we're not as far as we promised maybe 15 years ago. We need measurements of the neutron and the proton, and measurements of the neutron are still behind, I would say. They're very challenging to perform. And we also need like observables for a large number of different reactions. So what's needed here, since we cannot see any of these signatures as peaks in cross sections or even in mass distributions, is partial wave analysis, and these efforts remain very challenging. So in addition to what Annika has shown already for ELSA, this is a table that represents the class measurements. The JLab measurements. You see all these different reactions here on the left side, starting with single meson reactions for the top part of the proton, for the bottom part of the neutron, and then all these polarization observables on the top. And what you see here is that we have in principle data wherever you see a check mark, there's data available, but only those in red have been published so far. And that is partially a manpower problem. And with the class 12 efforts ongoing, the community has partially moved on, and there's tons of data available that still needs to be analyzed, and there's a small risk that that will never happen. So I think that one thing that the baryon spectroscopy community should do is get together and identify really the important measurements that still should be done in order to move the field forward. I think this is desperately needed in order to properly dedicate certain efforts to certain reactions. So that's sort of the status, and at this point, within the class collaboration, efforts are still ongoing for omega production and for some of the hyperon channels, the K lambda and the K sigma. At this point, there's very little going on for single pi and single eta. from class, which is different, as Annika said, at ELSA at the moment. Okay, so in terms of the spectrum again, there has been a lot of progress. So we've mapped out the second excitation band to a large extent. So you can compare here the 2010 to 2019 listings of the particle data group. Some resonances have been removed, some have been added. And from what I can see, moving on to this little table here, we're essentially, what I can see, we're missing 2 resonance or 2 good candidates. That doesn't mean that these assignments are all correct, but we're missing 2 candidates at the moment to complete at least the nucleon aspect of these multiplets. And then all bets are off at the moment when it comes to any other member of these multiplets, starting with the singly strange hyperons. And when it comes to the doubly strange candidates, we hardly know anything about these states. And that's where sort of at Jefferson Lab, the community has moved to, like in terms of the experimental efforts, at least, is to look at these doubly strange baryons. Okay, so just some highlights of accomplishments. You see here, one of the very first resonances that was identified was the N-star 1900, the old P13. And still to the very day, this is the way we identify baryon resonances. You can see here partial wave analysis in this mass range without the P13. These are polarization observables where we're looking at the transfer of circular polarization to the outgoing baryon, the polarization transfer, like perpendicular and within the scattering plane. And you see that the partial wave analysis can describe the data much better if the P13 is included. So this is sort of the way we identify or find evidence for new nucleon states. So it's within partial wave analysis. We're not observing any of these states directly. And this state was interesting because it sort of ruled out at a very early stage the traditional point-like quark-diquark oscillations. Okay, for the deltas, less has happened than for the nucleon resonances. To my knowledge, only 1 state has been updated here, the 1940 state. Other than that, not much has happened really for new delta states. And these are resonances that can be accessed more easily at ELSA, looking at these double meson reactions that Annika has already mentioned. So let me skip over this. Annika has already talked about the 2 meson states. This is the K plus lambda that was published by Klaas a couple of years ago. So here new N stars were needed to describe these data, just as an example. So this is the beam asymmetry and the target asymmetry. The data are somewhat less exciting. They're all these polarization observables to some extent, are all wiggles. For the outsider, it may be sometimes hard to really appreciate these data. For omega, this is the helicity difference. Here, a new 1895 nucleon state was established. So the rule of thumb was that with each addition of a new polarization observable, we came closer to confirming one of the nucleon states. So that's sort of what happened in recent years. Okay, so let me come back briefly to the fact that nothing or very little is known about the spin parity assignments. So I always like to highlight the spin parity measurement of the lambda 1405 that happened at Klaas, where we confirmed the 1/2 minus. That was a dedicated effort, and I hope that more of these measurements come out in upcoming years. Let me just flash a few efforts that are ongoing. So this happened at Klaas. Also, line shape measurements of the 1405 were published by Klaas a few years ago, and there are ongoing efforts at the moment at GLUAX to complement the Klaas effort that heavily centered on the charge decay modes, sigma plus pi minus and sigma minus pi plus. So GluX is currently performing measurements looking at the decay into sigma 0 pi 0. So we just had a round of talks for upcoming the spring meetings of the American Physical Society. So these results will come out in a while. Differential cross sections have also been measured for the 1405 and the 1520 by class a few years ago. So these efforts are also repeated partially by the GluX collaboration now. And as a first highlight, GluX has just published the spin density matrix elements for the lambda 1520 to understand better the production of the 1520 in photo production at high energies, of course. So this is a publication that came out just a month ago with much improved statistics over class, or class hasn't measured the spin density matrix elements, but GluX can repeat partially the cross-section measurements with much improved statistics. And that is nice to see. So we can really like now be able to sit off some of these resonances and study individual resonances with much better precision. What's also interesting to note, so I was talking here about the lambda 1405, lambda 1520. I noticed recently that many of the excited lambda states, for example, the 1670, that none of these excited lambdas, that none of the masses and the width had been measured directly previously. So there was a publication that came out last year of the Bell collaboration, where for the very first time, the lambda 70, the 1670 was observed directly in the mass spectrum, and a Bright-Wigner fit is now listed by the particle data group. All other, there are plenty of results listed in the particle data booklet, but all are based on partial wave analysis. And this is the very first measurement of the very first direct measurement of the mass and the width of the lambda 1670. And I think this is true for many other excited lambdas, where I hope we can make some progress in upcoming years. So as a highlight, this is again from the GluX collaboration, the Ada lambda invariant mass. This is just a fraction of the data that is available, but you see clear structures here for also for the 1670 and for other excited lambda states. So the hope is that we can like isolate some of these resonances with GluX data and study some of these states directly, which at the moment have come really all out of partial wave analysis. So that is interesting to note, and something where we can make progress in the future. So it is interesting also for some of the nucleon states. I've seen mass distributions where we can directly isolate some of the excited nucleon states. For example, I don't have a picture for that, but the N star, the 1535, is observed directly in the mass spectrum. And also for the hyperons, that leaves the opportunity to look for some of the rarer decays maybe of some of these baryon resonances, for example, radial decays. So that's a prospect that we're looking into at the moment, and that will probably move our field forward in the future. Just to wrap this up, I'm talking about the nucleon spectrum, what has happened of the neutron. There have been measurements, but in a summary that no new nucleon resonance has been identified in any of the reactions of the neutron so far. Certainly some of the known resonances, helicity amplitudes were determined, but in terms of the spectrum, no nucleon states have been identified in any of these neutron reactions. There are a few measurements, a few analyses still ongoing at JLab, and I think some are planned at ELSA. So we've learned something, but not in terms of mapping out the spectrum. So Annika has shown this table already. Everything highlighted in red here is based on photo production. So we can truly say that we've made a lot of progress in recent years. But it's still also obvious that some of the states that we've advertised early on, like the K lambda, K sigma reactions, are still underexplored, and that there's probably still a lot we can learn from these states if we analyze the data that are available. And the same is true also for omega decays. We've learned a lot from that decay, but you see that states are fairly underexplored in this decay mode. Okay, let me briefly move on if I have still like a couple of minutes. The cascades, the doubly strange resonances. So far I've talked only about the nucleon states in the multiplets. That's all sort of we've done in recent years. Of course, it's important in order to establish the systematics also to look at the other members of these multiplets, and efforts have shifted a little bit towards these doubly strange cascade resonances. So what I've listed here, these cascade resonances, they are part of the octet and the decouplet. So there should be as many cascade states as there are nucleon and delta states combined. So we have the 1320, that's the octet ground state, and the 1530, which is the decouplet ground state. And then what you see here is below or at like 2 GeV in mass, there are 5 states known only and listed by the particle data group. And all of these states have been observed directly in the mass spectrum, in the corresponding mass spectra. So
yes, you have 5 minutes now.
Okay,
5 minutes. Yep.
Yeah, that's all right. So all of these states have been observed directly in mass spectra and are expected to be substantially narrower than the nucleon states and should be more easily analyzable. What's intriguing, though, is that even at these low masses, we're missing 2 states entirely at the moment. So only these 5 are listed here. And if we look into the first excitation band, so I'm not even talking about the second excitation band that I mentioned earlier for the nucleon resonances. So we're talking about the very first excitations here with negative parity. We're expecting like decouplet members and 2 octets. And that would in total give us 7 states, and only 5 are known at the moment. They're not even candidates or hints for any of the other 2. And since they're narrow, it's really interesting to understand. It would be interesting to understand what is going on here. So this is one of some of the efforts that we're looking into at the moment. You see here in this little table, there has been always that controversial discussion about 2 states, the cascade 1620 and 1690. The 1620 has always been listed only as a 1-star resonance. And this has been sort of solved. So there was a hint for the 1620 here in earlier class data, but it was not statistically significant. And just recently, the Bell collaboration has come out with new measurements where a clear signature for the 1620 is observed in addition to the 1690. So this resonance should be upgraded in the future. What's interesting is that the 1620 is very broad, appears to be much broader than the other 2 states. So what we want to do really is find analogous states to like the lambda 1405 or the Roper resonance, like in the other sectors here. And that would like give us a much better understanding about the systematics of the spectrum. So this is intriguing, and Bell has like looked into the cascade pi invariant mass. What we've done at GluAx is to look into the lambda k decay mode, and this is what you see down here. So if a doubly strange cascade consists of 2 strange quarks and a U and a D quark, then we would expect an excitation between the 2 strange quarks to decouple from the pion decay. And for that reason, we looked into the K lambda decay mode. And indeed, if we do that, we see a prominent peak here for the 1820. But interesting enough, that's the only statistically significant signature that we see that suggests that the 1820 may be indeed the excitation between the 2 strange quarks here, but nothing else is observed. And we know that we were all excited about the idea 10 years ago to look for cascades in photoproduction, where we would expect like all of these states to line up in the mass spectrum. And like a very first conclusion is that that is not the case. So the 1820, in addition to the ground state, is really the only excited cascade that we observe at the moment, and that's interesting. Okay, so just wrapping this up, I'm not going to talk about these heavy flavor states. So a lot has come out of the the LHC. In particular, LHCb has published an enormous amount of data on new states for mesons and for baryons. And as I mentioned earlier, unfortunately, from an experimental point of view, this is the high energy community, and I think we need to talk to each other a little more than we have in the past. And then the doubly charmed, we heard about that already in the earlier session, so I'm not spending any more time on that. The one thing, and I'm going to finish up with this, is the observation of the pentaquark at LHCb. In J-psi proton, one measurement that I would like to highlight is that we tried to look for this state also in GLOX, in photo production, where we would observe, so the J-psi would be produced in gamma proton reactions, and the pentaquark would be observed in gamma proton reactions. And that should be close to the threshold in GLOX data here. But at this point, we have observed, so there was a publication that came out like 2 years ago. So we have not observed any signature for the pentaquark in photo production using GLOX. So these measurements will be repeated with substantially more statistics. So stay tuned on further results on that. Okay, so with that, let me finish up. I think my time's up. So we're still interested in these fundamental questions. What are the relevant degrees of freedom in excited baryons? Something that Annika touched upon. Can we identify unconventional states like the Roper, the 1405? Can we identify any of these states in the strangeness sector? Can we identify any of the cascade states that behave similarly to the 1405 or the Roper resonance? I think that would be an interesting question. What's the nature of non-quark contributions, meson baryon cloud, or dynamically generated states? I mean, at one point we have to come together with all these pictures and understand the data and putting that all together with the ideas that are out there. And yeah, so the fundamental question, of course, how do nearly massless quarks acquire mass? But that's a fundamental question, not necessarily only related to baryons. So let me finish here and open the floor for some discussion.
So thank you very much. So I clap for all the others. That's the sadness of Zoom workshop. So Christoph has a question I see here. Please, Christoph.
Hi, Volker. Thank you very much for this very nice talk. Can you go to this Roper discussion? There weren't any slide numbers, therefore I cannot give you the slide number.
That was intentional to confuse everybody. This one here?
Okay. Yes. You see, when I look at the pionucleon phase shifts and inelasticities, the Roper must have a strong connection to pi n, in particular to sigma n, because it basically drops like a theta function, the pi n elasticity at the Roper close to the Roper mass when the sigma n channel sets in. In the calculations, if I recall correctly, however, that refer to the curves on the very left side, the sigma nucleon channel wasn't even included. Therefore, I'm a little reluctant against buying this conclusion so straightforwardly. But now I have a question, not only a remark. How do you really identify in these transition form factors that what you look at is the Roper? Because the Roper is in the, if you just do pionucleon scattering, the Roper only comes about, as the many other states you mentioned, just through the partial wave analysis. Therefore, what is really done to really identify the Roper contribution in the transition form factors? And how difficult is it?
It is certainly difficult. So I mean, this is electroproduction. And you certainly have to know that the resonances are there. So electroproduction of these like experiments are not good for finding any new states, for example. I think some confidence is giving by analyzing different channels and comparing results. And some of that is also model dependent. So in this case, the pi, and I acknowledge your comment that the sigma channel was not included here. But in this particular case, I think to answer your question, the confidence is based on analyzing, for example, the 2-pion and the single pion channel and arriving at consistent results. I think that gives us the confidence, to be honest. Other than that, you're absolutely right. This is challenging, and results are still based on like, to some extent, on partial wave analysis. I agree with that.
Okay, thank you very much.
Does that answer your question?
Well, at least it doesn't remove my skepticism concerning the conclusion.
Yeah, I don't think I can completely remove that, but I think really the confidence in what we're doing here experimentally is on the comes from the comparison of different channels. If that wasn't consistent, then yeah, that would be concerning.
So while other people think about additional question, I had a question that is on the measurement of class lambda p. So the cross section and the comparison with hypernucleon potentials. Do you know if there are or there will be any attempt to compare these results with what Alice, for example, got out? So they have done, I don't know if that, so there is a community, is completely different community who is trying to do that with the proton-proton data, right? And then looking at correlations between proton and, I don't know, omega and all the rest, and then trying to see what potential fits better from all QCD and so on. I think it would be interesting just to compare the two results.
Yeah, to answer your question, I don't think that the comparison is going to happen. So this was sort of a feasibility study within class, and the student has graduated. There was just one group doing this measurement. And at the time, I hadn't paid little attention to that, but I've noticed that there is like interest in other communities. And that has sort of triggered the idea, at least in my group, to repeat the measurement, like with better statistics, with GLUAX data, extend the momentum range here, and maybe also look into the possibility of using other hyperons. So to answer your question,
context would be great if you then get in contact with the Alice groups doing that, because I think that if one wants to tackle this business of equation of state, we need to address that from many different communities. So if they
I would love to talk to you about that, or to any other person that you can get me in touch with.
Not in Alice, but I know people who are in Alice.
Yes, I mean, one thing is like repeating this measurement is extremely challenging, and this is not really the core of the spectroscopy community. So what really I would like to do before I, for example, put an entire like thesis on this is to fully understand what the interest is, and maybe even what is it that the other community wants us to measure. I mean, is that the cross section? Is there something else that is more interesting? So I'm personally highly interested in talking about that.
So we organized that separately. I think that was then a good question, at least a good feedback. So are there additional questions for Volker? It does not seem to be the case. So thank you very much again for this very nice talk. And we move on to the next talk, and that is Heinz Clement.